In this video, we will cover sections 7.5 to 7.6 in the textbook. Remember that these videos are meant to supplement your readings for class and additional classroom lectures with your instructor. I would advise using the provided R Markdown file to follow along with the video. When there are violations to the assumptions for a linear model, then we cannot trust any of the inferences generated by the regression model. There are three potential solutions to violations of the validity conditions. Remove an offending point or two, one at a time, to see if this improves the results. Transform the response, the explanatory, or both variables to see if you can force the dataset to meet our simple linear regression assumptions after transformation. Consider more advanced statistical models that can account for these issues. In this video, we will focus on the second solution, transformation of the response, explanatory, or both variables. We will also work through an example to see how to interpret slope on both the original scale and the log transformation scale. Transformations involve applying a function to one or both variables. The book discussed both linear transformations and nonlinear transformations. In linear transformation functions, we change the scaling of the variables but not their shape or the relationship between two variables. Linear transformations will not help fix assumptions in regression situations. Nonlinear transformation functions apply a function like a log or power of the original variable. We will focus on nonlinear transformations in this video. In scenario 1, we will apply a log transformation to only the response variable. In scenario 2, we will apply a log transformation to only the explanatory variable. And in scenario 3, we will apply a log transformation to both variables. In a log transformation, the log is applied to each value in the dataset for the variable being transformed. Looking at the box plot of the data can give you an idea of which transformation to use. If the distribution of the explanatory variable is right skewed, then consider log transforming the explanatory variable. If the data has a curvilinear relationship, log transforming the response variable may work to linearize the relationship and reduce non-constant variance. Let's work through an example with a dataset collected in 1988 on the rates of infant mortality, infant deaths per 1,000 live births, and gross domestic product, or GDP, per capita measured in US dollars from 207 countries. Using the R output, we can find the estimated line of regression. So for this dataset, our slope is negative 0.0009, and our y-intercept is 41.378. So our estimated line of regression shows the estimated infant mortality is equal to 41.38 minus 0.0009 times the GDP. Remember, to interpret slope, we discussed the expected change in y for a 1 unit increase in x. So for this data set, we see that for every increase in $1 in GDP per capita, the expected infant mortality decreases, our slope is negative, on average by 0.0009 infant deaths per 1,000 live births. Is this simple linear regression model a good fit? Let's look at the diagnostic plots for this study. When checking linearity, we'll look at both the scatter plot and the residual versus fitted plot. We can see a very curvilinear pattern to our data on the scatter plot and the residuals versus fitted plot. These show evidence of a violation of linearity. For constant variance, we need to look at the residual versus fitted plot to assess constant variance, since we have a curvilinear pattern in our data. It is kind of hard to distinguish whether or not we have issues with constant variance or just a problem with linearity. Looking at the normal QQ plot, it appears that the distribution of the residuals is right skewed. There is evidence against normality. When assessing whether or not we have influential points, there does seem to be one value out here with a Cook's distance greater than 0.5, showing moderate evidence against no influential points. So it appears that the simple linear regression model is not a good fit. Let's start with a log transformation of the response variable, infant mortality. To help us understand how to interpret slope with transformation, the book steps through the math behind the transformations. To interpret slope for a transformation of the response variable, we can look at both the interpretation on the log scale and the original scale. To interpret on the log scale, we see that for a 1 unit increase in x, the explanatory variable, we estimate a slope change on average in log of the response. For the original scale interpretation of log x, we see that if our slope is greater than 0, for a 1 unit increase in x, the median of y is estimated to change by e to the slope times. To convert into a percentage increase, we take 1 minus e to the slope times 100%. For a 1 unit increase in x, the median of y is estimated to increase by 1 minus e to the slope times 100%. If our slope is less than 0, for a 1 unit increase in x, the median of y is estimated to change by e to the slope times. Now we'll convert into a percentage decrease. 1 minus e to the slope times 100%. For a 1 unit increase in x, the median of y is estimated to decrease by 1 minus e to the slope times 100%. Returning to the GDP dataset, we find the estimated regression equation. The estimate of the log for infant mortality is equal to 3.479, our y-intercept, minus 0.00005, the slope, times GDP. To interpret on the log scale, we see that for every $1 increase in GDP per capita, we estimate a negative 0.00005 log deaths per 1,000 births per $1 change on average in infant mortality. Before interpreting on the original scale, we need to find e to the negative 0.00005, our slope value. Because the slope is negative, the change on the log scale is negative and shows a percent decrease. For every $1 increase in GDP per capita, the median deaths per 1,000 live births is estimated to change by 0.99995 times less deaths. Or, for every $1 increase in GDP per capita, the median deaths per 1,000 live births is estimated to decrease by 0.005%. Did the log transformation of infant mortality help the fit of the model? We can see that there is still a curved linear pattern in our scatter plot, and it appears that this transformation helped with the normality assumption, but it did not fix the issues with linearity. Next, we will use a transformation of the explanatory variable. For a log scale interpretation, we see that for a 1 log unit increase in x, we estimate a slope unit change in the mean of y. For our original scale interpretation, for a doubling of x, we estimate a slope times log 2 change in the mean of y. Returning to the GDP dataset, we find the estimated regression equation. Our estimated infant mortality is equal to the y-intercept, 155.7698, minus the slope, 14.86, times the log of GDP. To interpret on the log scale, we'd say for a 1 log dollar increase in GDP per capita, we estimate infant mortality to change, on average, by negative 14.86 deaths per 1,000 live births. Before interpreting on the original scale, we need to find the slope times log of 2, which is negative 10.3. For a doubling of GDP per capita, we estimate infant mortality to change, on average, by negative 10.3 deaths per 1,000 live births. That is, the mean infant mortality is reduced by 10.3 deaths per 1,000 live births for each doubling of GDP. Did the log transformation of GDP help the fit of the model? Looking at our scatter plot, we can see that this transformation helped a bit with linearity. Our residual versus fitted plot shows the same, but now we have evidence against the normality assumption. We have a right-skewed distribution. Next, we will look at a transformation of both variables. For a log scale interpretation, for a 1 log unit increase in x, we estimate on average a slope unit change in the log unit of y. For the original scale interpretation, we have two options. We can say for a doubling of x, we estimate a 2 to the power of slope multiplicative change in the estimated median of y. Or a 1 minus 2 to the power of slope times 100% increase or decrease in the estimated median of y for each doubling of x. Returning again to the GDP dataset, we find the estimated regression equation. The estimated log for infant mortality equals 8.104 minus 0.617 times the log of GDP. To interpret on the log scale, we'd say for a 1 log dollar increase in GDP per capita, we estimate on average a change of negative 0.617 log deaths per 1,000 live births in infant mortality. Before interpreting on the original scale, we need to find 2 to the power of the slope, and this is a value of 0.652. On the original scale, for a doubling of GDP per capita, we expect a 0.652 multiplicative change in the estimated median for infant mortality. That is a 34.8% decrease in the estimated median infant mortality for each doubling of GDP. Did the log-log transformation help the fit of the model? It appears that this model is the best fit. Looking at the scatter plot, we see a nice linear relationship between our variables. Looking at the residual versus fitted plot, we have little to no evidence against linearity, constant variance, and we see no issues with influential points. We can see that there's a little bit of evidence against normality. The tails of the residuals are a little heavy, but this is the best fit for our data set. We use transformations when we have violations of the assumptions for linear models. If we have issues with linearity, normality, constant variance, or if we have influential points. Use the transformation that fits best in regards to the diagnostic plots. Remember that when using transformations, the interpretations change depending on the type of transformation.